Okay, Assalamualaikum warahmatullahi wabarakatuh. Welcome back. Now we are going to cover the topic of dynamic, okay, which is a kinematic of particles. Okay, so I would like to advise you to pay a lot of attention, especially on the kinematic of particle, because it is the fundamental of all. Okay, fundamental of dynamic. Because if you have very strong foundation of this topic, inshallah later on when we cover the other aspect, which is kinetic of particles, kinematic of rigid body in 2D and 3D, you will have no problem. So do not honeymoon for this first 7 weeks. So I would like to advise you to do a lot of exercises and strengthen your fundamental. Okay, and inshallah if you do what I say, you do exercise on your own, you discuss with your friend, and then you try to do on your own, inshallah at the end of the day you are going to get you are going to reap the hard work that you have done. And now we are using Bias and Johnson book. Okay, um, chapter 11, the topic of kinematic of particles. Okay, as I mentioned earlier, these are the coverage of kinematic of particles. Okay, going to cover rectilinear motion, curvilinear motion, relative motion, and the dependent motion. Okay, these are the topic of kinematic of particles. Okay, and this slide 4, what I'm trying to show here is this is CO1 types question. Okay, you should be able to differentiate between kinematics versus kinetic. Okay, what is the difference? Okay, should be able to differentiate. Okay, because kinematic here we study about motion. Okay, and then kinematic we study about the relation of the existing between forces acting on body, mass, and motion of the body. Okay, um, and these are the different type of motion. First thing I mentioned just now, rectilinear motion, which is move along a straight line. And then the second one, we talk about rectilinear motion. This is straight line, and then this one we have, okay, the particle move in a curved line. Okay, 2D or 3D. So basically, we talk about position, talk about velocity, talk about acceleration. So dynamic don't have many complicated equation like other subject. Okay, these are the three items that we are looking at, or we are dealing again and again. We talk about displacement, talk about the velocity, and talk about acceleration. These are the possible coordinate system I have mentioned in our previous class, previous topic. Okay. Okay. Um, so I don't want to elaborate more about this one. I have explained. Okay, we straight away go to this one. Rectilinear motion, position, velocity, and acceleration. Okay, so look at this one. Particle move along straight line. Okay, so keyword is straight line. Particle move along straight line. So it is called rectilinear motion from zero. Okay, so we have like a ruler here. Take one as a datum. Okay, 1, 2, 3, 4, 5. So this is P. So every unit of this one, the scale is 1 meter. 1 meter, 1 meter, 2, 3, 4, 5. 5 meters. Okay. Datum again. This is to here positive. So here, going here, this is plus. So this is negative. So P prime, which is X prime. So this is minus. -1, -2 meter. So position and then distance. Remember position P positive 5 meter and the distance is 5. Position to the right is positive. So unit vector here is I. So I will say this is positive 5 I meter unit. And then here position is -2 meter I. Right? So in the tutorial or assignment that I have given to you, the way we show you to make sure you really understand every item that I have mentioned just now. Okay, position coordinate, positive or negative. So I have mentioned just now the datum. You set the datum. You are the one who will decide the datum. If you decide datum is here, okay, to the right is positive. To the left is negative. Okay, based on a fixed origin data. We call data. Okay, can call datum, can call origin, can call 00. Okay, any name, yeah, which is which are the same. Okay, okay, what is this? Okay, okay, I hope you also have a textbook with you. Okay, I'm referring to the textbook Bias and Johnson. Okay, now we have the graph here. Okay, the graph. Okay, we have the graph. Motion of the particle is known. With the position coordinate, motion of the particle we can express in the form of the function x equal to 6p pi minus p cube and the form of graph x versus time. Okay. So you plot the graph 60, so you have p minus 60 square. So 60 square, so 1 minus t. Okay, 1 minus t. Or this one x. Okay, 60 square minus this is 6. So you put t, this is the easiest to put t and keep, okay, this is 6. So t square minus, okay, t square. So 60 square minus t square t, keep. Okay, so you get 6 minus. So you can factor out again. So after that you can plot the graph. How to plot the graph for velocity, and then how to plot graph for acceleration. You can plot the graph by differentiating this function, okay, with respect to time. So you differentiate this one with respect to time. Okay, 12t minus 3t square, and then for acceleration you get 12t. Okay, 12. This is 12 minus 60. Okay, so this is for acceleration. This is the velocity. Okay, and this one is for position. Okay, so 60 square minus t cube, 12t minus 3t square, and then you get 12 minus 60. Okay, so from there you can plot the graph. Okay, you plot the graph. of this one. Okay. Next slide, what I'm going to show is the concept of average velocity and instantaneous velocity. Okay, so we have here again the data p and then p prime. Okay, so p prime. So at first position you have a time. Okay, this is p. Okay, then after a few seconds you add another one. You have another position. Okay, so to find the average velocity, basically v average equal to, look at here, this is x, from here to here is delta x. So delta x divided by delta. Okay, this is average velocity. So how about instantaneous velocity? Okay, so instantaneous velocity basically can find the limit of this one. Okay, so limit from t goes to 0, so you differentiate this one, limit, which is a delta x, delta t. Basically delta x, delta t basically is the fundamental of differentiation. Another thing that I would like to mention here also is about the concept of instantaneous velocity. The instantaneous velocity can be positive or can be negative. Okay, instantaneous velocity can be positive or can be negative. So to the left over here, 0, and then to the right over here, which is velocity greater than 0, so this is positive. Okay, and the magnitude of velocity is referred to, okay, this speed. Okay, what is the speed, for example? So magnitude of velocity is a particle speed. Okay, all right. We have plot the graph of x just now. Now we want to see what is how the velocity graph looks like. Okay, this one we have 60 square minus p cube. So differentiate respect to time, you get 12 minus 30 minus 3p square. Okay, so you equate all of that to 0, so you have 0, 4, okay, and then you have minus 36 here, you substitute, so the graph is going to be like this. Okay, so before that, after we have the value of this one, instantaneous velocity, so basically limit delta x delta t is basically dx. Okay, dx, and then we proceed to relate with acceleration. Okay, same thing, relate with acceleration. We have just now the value of x. Now we substitute this with the value of y, the value of v, sorry, value of v, particle with velocity v. So v, and then here v plus delta v. Okay, and then going to have the instantaneous acceleration. So a equal to limit delta v delta t. So this is what? dv dt. Okay, so this one we're going to use again and again. Just now dx dt, this time dv dt, which is acceleration. Okay, for instantaneous acceleration, positive. We call it positive. It is positive when we have the increase in velocity. Okay, increasing positive velocity, so it is positive. Okay, how about this one? If this one is negative, decrease negative velocity. Okay, so we're going to get decreasing negative velocity. Okay, decreasing. How about this one? Negative positive velocity. There are three different few other cases. And then this one, this case, it increasing negative velocity. Okay. And then we proceed by relate this one. We have here dv dt, and acceleration also can be written as d square x dt square. Okay. Now we want to plot the graph of the acceleration. We differentiate this equation with respect to time. We get 12 minus 60. So it is a linear graph minus slope, and then intersect at positive 12. So you get this this graph, acceleration versus time. Okay. So in short, what happened here? What we have done just now, the graph can be plotted. Okay, from this particle by looking at this figure. Okay, you can plot the graph of displacement, velocity, and acceleration. It's different, right? This one t square. Okay, this one minus t square, so minus, and then this one is linear, yeah, with minus slope. Okay. All right. This is from section 11.2 from the book. This one, what we're trying to show here is, this is what we call initial condition. Initial condition, what will happen if t equals 0? If t equals 0, x equals 0, you substitute. When t equals 0, x will be 0. Keep going. Yes. Where are we now? Okay. Okay. When t equals 0, v also 0. And when t equals 0, acceleration is 12. Okay. Next boundary condition, which is t equals 2 seconds. So you substitute 2 into these three equation, you're going to get 16 meter. Maximum velocity is 12. Okay, which is here, maximum. And then acceleration is 0. Okay. What else? Okay, how about 4 seconds? 4 seconds. At t equals 4 seconds, you substitute, you get the maximum x here, 52 meter. And then velocity is 0. And then you have minus 12 meter. Okay, here. Okay, what else? How about 6 seconds? You substitute at 6 seconds. This one you can do all of this using Microsoft Excel. If you want to try to substitute the value, so you get 0 at 6, and then velocity minus 36, and then you have here acceleration is 24, 12 minus 6 times 6, 36, minus 36, so you get minus 24, yeah? Minus 24, okay. Okay, this slide just only show you the concept of motion, motion of particle. Because when you are dealing with this type of problem, motion of the particle, motion of particle is known if position is known for all time t, okay, and then there are three classes of motion, okay, three classes of motion. So when solving dynamic problem, we have three classes of motion. Case number one, acceleration as a function of time. Second one is acceleration as a function of position. Okay. And then the third one is acceleration as a function of mv. Okay. So this one as a function of time, which is as a function of position, and then this one is a function of velocity. Okay. So we're going to have different type of technique to solve this one, to integrate, for example, log. So you have to revise how to integrate log later on, natural log, or when we're dealing with this type of motion. Slide 11 just show you how to do the integration, okay, for different function of time. This one, given function of time f, acceleration equal to ft, okay. Just to show you how to do. Starting from this one, we know that dv dt equal to acceleration, and then acceleration as a function of time. Starting from this one, and then we cross multiply. Okay, so you get dv equal to ft dt. Okay, from there, and then what you need to do then, you integrate both sides. Okay, integrate both sides. This one, the limit from v0 vt, and then you have from 0 to t. Okay, and then you solve this one, you get integrate dv, you get v, so you get v vt minus v, okay, from here. And then this one, you do the integration of ft dt, okay. So the time limit is from 0 to t, okay. All right. Same thing for the next one, which is just now the velocity. This time is x, okay, dx dt equal to vt, okay. Again, same thing you do, you cross multiply, so you get dx equal to vt dt, and then you integrate both, okay, limit x dot to xt, then here from 0 to t. So what you can to get here is you get xt minus x dot, okay, and then this is the integration, integration of vt dt, okay, which is this one. Next one is the acceleration, same technique that you can use. This is the case for acceleration as a function of time, and this is the case acceleration as a function of position, which is a equal to f of x, okay. So same technique you can do the way we do the integration, okay. Starting with this one, cross multiply, and then we start to do the integration, okay. And then the last case, which is expression as a function of v. Okay, same thing, starting to write dv dt equal to a, which is fv. Okay, all right, and then you do the integration of this one for both sides. Okay, and then you will get the value of x in terms of the integration of v dv minus fv. Okay, so in a nutshell, these are the three common classes of motion, which is I mentioned just now. What we are doing here is the first case, which is a as a function of t. Okay, expression as function of time. Okay, case number 2, what we are doing is a as a function of x, and then the third case we are doing is f, a function of of b. These are the three cases that we are doing. Okay, so what we are going to do, I want you to go through, on your own, do this example. Okay, example 11.2. Okay, 11.3. Okay, 11.2, 11.3. Okay, what else? Yeah, just do 11.2 and 11.3. Okay, for your own exercise. Okay, do you have any question before we finish our class for today? Any
No,
question?
no, bro.
So far, no.